Hello, everyone. We are Junuk, Jihyun, and Hanmu. I will present our work, OpenFS, multi-hand capable fingerspelling recognition with implicit signing hand detection and frame-wise letter condition synthesis. In this work, we address three major challenges in fingerspelling recognition: signing hand ambiguity, the peaky behavior problem caused by CTC-based training, and the out-of-vocabulary problem. Fingerspelling is an important component of sign language where words are spelled letter by letter using hand poses. However, recognizing fingerspelling in real-world videos is still challenging. In this example, the right hand is the true signing hand, but the left hand shows larger motion changes. Existing method uses signing hand detection based on hand motion changes. As a result, the existing method incorrectly selects the left hand and fails to recognize the word. In contrast, our method directly takes the multi-hand pose sequence as input and predicts the letters NAD. As shown in the attention visualization, our model naturally focuses on the correct hand while predicting the letters N, A, and D. It can implicitly identify the signing hand through cross-attention. Another limitation of previous approaches comes from the CTC loss. CTC-based training often produces what is known as peaky behavior, where only a few frames strongly contribute to prediction. This results in weak temporal representations. Here, we visualize frame-wise similarity maps of encoder features. PoseNet struggles to capture meaningful temporal structure and mostly predicts only one dominant feature pattern. In contrast, our method learns semantically rich representations across frames, enabling better discrimination between different letter poses. Blue, red, and green borders indicate frames with similar features to the letters A, S, and L, respectively. Another challenge is the out-of-vocabulary, or OOV, problem. Since new words continuously emerge, collecting fingerspelling data for all words is difficult and expensive. Now let me explain our recognizer architecture. We adopt a transformer encoder-decoder framework. The input is a sequence of right and left hand poses extracted from videos. The pose sequence is first embedded into a feature space, and then encoded using our proposed dual-level positional encoding. Unlike standard positional encoding, our encoding separately represents hand identity information, such as right or left hand, and temporal position information. This enables the model to distinguish different hands while preserving temporal consistency. The encoded pose features are processed by transformer encoder layers. At the decoder side, letter tokens are embedded using a letter embedding layer. The transformer decoder attends to both the encoded pose features and previously generated letter tokens. Using cross-attention, the model learns the relationship between hand poses and output letters. Finally, the output head predicts the next letter token autoregressively until the end token is generated. Next, I will introduce our frame-wise letter condition generator for OOV fingerspelling synthesis. The generator takes a noised hand pose sequence as input. The noised hand poses are first projected into a feature space using a pose embedding layer. At the same time, the input letter sequence is embedded through a letter embedding layer. The pose embeddings and letter embeddings are concatenated frame-wise. This enables the model to directly associate each frame with its corresponding letter condition. We additionally provide the diffusion time step embedding to the transformer encoder. This embedding indicates the current denoising step during the diffusion process. We then add positional encoding to preserve temporal ordering across the sequence. Finally, the transformer encoder predicts the clean hand pose sequence from the noisy input sequence through iterative denoising. As a result, our generator can synthesize realistic fingerspelling pose sequences for arbitrary words. To improve recognition, we introduce two auxiliary losses: the signing hand focus loss and the monotonic alignment loss. First, the signing hand focus loss uses the cross-attention map between hand pose tokens and output letter tokens. We aggregate the attention values for each hand separately. From this, we compute the handwise attention distribution and its entropy. Minimizing this entropy encourages the model to focus on a single dominant signing hand. Next, we introduce the monotonic alignment loss. We first construct a cumulative cross-attention map to analyze temporal alignment between pose frames and output letters. We then compute the monotonicity violation map. Positive values indicate cases where later letters attend to earlier frames, violating the natural temporal order of fingerspelling. By minimizing these violations, the model learns smoother and more temporally coherent attention transitions during recognition. This figure illustrates our coarse framewise letter annotation method. The black regions indicate frames with no matched letters, the blue regions indicate frames matched with one letter, and the red regions indicate frames matched with multiple letters. Using the processed cross-attention map, we assign coarse framewise letter labels to the hand pose sequence. Using the processed cross-attention map, we obtain coarse framewise letter annotations for the hand pose sequence. Each frame is assigned either a corresponding letter label or a blank label. To refine these noisy coarse annotations, we train a framewise annotation refiner using the encoder features from the pre-trained recognizer. The refiner predicts framewise letter labels for each pose frame. As shown here, the refined annotations become more accurate and temporally consistent compared to the coarse annotations. Here, we compare our method with previous RGB-based approaches and the pose-based method, PoseNet, on Chicago Fingerspelling Wild CFSW, Chicago Fingerspelling Wild Plus CFSWP, and FS-Neo. Our method consistently achieves the best recognition accuracy across all benchmarks. In particular, on FS-Neo, which evaluates generalization to unseen and newly emerging words, our method significantly outperforms PoseNet, demonstrating strong OOV generalization capability. We also observe that the additional synthetic data generated by our framewise letter condition generator further improves the performance of both PoseNet and our recognizer. These results demonstrate the effectiveness of both our recognizer and our OOV data generation pipeline. Here, we show fingerspelling pose sequences generated by our framewise letter condition generator for the word Denver. The generated sequence demonstrates realistic finger articulations and smooth temporal transitions across letters. To conclude, we presented OpenFS, an open-source framework for multi-hand-capable fingerspelling recognition and generation. Our method enables implicit signing hand detection and improves temporal alignment through the proposed auxiliary losses. In addition, we propose a coarse-to-fine annotation pipeline and a framewise letter condition generator for OOV fingerspelling synthesis. Thank you for listening. If you are interested in our work, please feel free to check our LinkedIn page and the OpenFS project page through the QR codes below.